Quantum is exciting because it's the perfect marriage of deep fundamental science and applications. On the one hand, we get to study why the world is the way it is, why these very strange properties happen when the world gets small or cold. On the other hand, we get to work on new technologies like communications, computers, and sensing that will be fundamentally transformed by applying quantum science. It's not every day that you find a field where you can work on both the mysteries of the universe and new technologies that will change the world. At the same time, quantum is a massively multidisciplinary field. On a daily basis, I'll talk to mathematicians, computer scientists, physicists, theoretical physicists, engineers, and all of us have to work together outside of our traditional silos in order to make this thing a reality.
So what really excites me about quantum? Actually, there are three things that really excite me about quantum. The first one is it works. It's this really counterintuitive behavior that's been predicted by physicists, and we can go into the lab and see this counterintuitive behavior, which to me is really just amazing. The second thing is that quantum has reached a point where quantum systems engineering is no longer just about the physicists. We need a lot of different experts to come together to build a bigger quantum machine, including software engineers, mechanical engineers, optical engineers, RF engineers, and we still need physicists. And then the third thing is that it's still unknown the impact that it will have. There's a few uses in cryptography and search that are provably better, but people are really clever and they keep coming up with new and really interesting ways to use these unique interactions that quantum gives us, and I'm really excited to see where it goes.
So the thing that excites me most about quantum is applying devices that are developed for quantum information science to answer some of the biggest questions in fundamental physics. One of these questions we particle physicists ask ourselves is, what is the nature of dark matter? And dark matter is a known form of matter that appears to make up 85% of the universe's mass. We know it's there from cosmological and astrophysical observations, but we do not know what type of particle it is. The community of particle physicists meets now for the first time that of quantum engineers to work together to reach common targets. We are using quantum information science tools to move particle physicists from big particle colliders experiments to small-scale tabletop experiments to understand our universe at the most fundamental level.
I use the advanced computational resources such as a supercomputer at Oak Ridge National Laboratory to solve the computationally difficult problems to design the next generation quantum devices. And from our daily experience, we know 4 fundamental phases or states of matter. They are solid, liquid, gas, and plasma. But there are many other phases under much more extreme conditions, such as superfluid, Bose-Einstein condensates, or quark gluons. And I personally am very interested in the new class of material. They are called the topological quantum materials. The discovery of the topological phase of matter was actually even recognized by the Nobel Prize in Physics in 2016. And we are using this cutting-edge science to develop quantum devices.
What really excites me about quantum sciences is that we are poised to unlock a new paradigm of computing and of communication. So using our newfound understanding of atoms and light and how to engineer those systems, quantum computing will allow us to do things like revolutionary drug discovery simulations. On the communication side, we'll be able to do things like send information in a fast and reliable, secure way using concepts like quantum entanglement and quantum teleportation. Being a part of this community is truly a privilege, sort of like how the science community studying transistors gave us digital computing in the modern age, so too will quantum computing give us something unknown, something that we can't predict yet. And we're all very excited to see where it goes.
The thing that excites me the most about quantum information science and technology is, first of all, the physics behind it, which is my favorite type of physics, and that's what I liked when I studied in the university, and so I decided to pursue it for my following career. And the second thing is that we're trying to figure out what kind of applications are possible using this type of physics, but there are many, many possible applications to what we're trying to develop, and I'm excited to see where we end up with this.
The challenges of building a working quantum computer are actually very large, but the potential ramifications of solving those problems will have far-reaching impacts both in the scientific community but also in wider societal contexts, such as the creation of renewable energy, pharmaceuticals, applications in national security, and even more fundamental issues such as economic and finance.
So what excites me the most about quantum technologies is that right now we have good enough understanding of quantum mechanics and quantum processes behind, good enough engineering to design experiments and engineer quantum states useful for certain applications, yet there is still a lot to do in terms of very fundamental discoveries to bring those devices, quantum devices, to its full potential. My particular interest is within quantum sensing, and that is what we are focusing within the project I am a PI of.